readable overnight. I think we need to make this a bit like a dartboard and non-sectional version. Is it readable? Okay. So, yesterday we were talking about music theory on the basis of transition systems, and due to the lack of time and Easter holiday, even I'm a bit messed up with data splitting on the basis of non-elementary transition systems. So as I indicated in the message on the Moodle, if there's time left before 2 o'clock, I will try to again explain that. Those interested at the same time, we will not apply that code in the exam. As I already indicated, we might ask you what the purpose of the data splitting would be, but we will not ask you to apply that over. And also, as always, I expect that I won't have time left. So, today we will talk about an alternative version of region theory-based learning discovery, which uses the notion of language. And I would briefly like to very fast recap why we still focus on using this type of discovery techniques as opposed to the magnificent inductive mining. And the example I gave you guys yesterday is like this. I will go through it very briefly. So we have this process model where we describe ordering, in this case, funds, and actually sending a reminder is a very conditional activity because we only want to do it if the invoice was sent, but the delivery was not yet prepared nor a payment was received. And then, as I showed you yesterday, we give an event log that just describes this behavior to the alpha miner, you get this model, which has several problems, has improper completion, because you can do a cancel order, and the token in this place will be remaining, and you can infinitely many times send a reminder. So what this process describes, so it's not what the actual process looks like, that generated the data that we use in this synthetic experiment. Similarly, in the inductive miner, the basic problem was if you use this data, essentially that you can skip payments, and skipping that payment, not doing the payment, in no way influences the cancellation of the order or the preparation of delivery. So the problem there is that this type of constructs is not expressible by process trees, which are the type of process models that the inductive miner returns. So in case I give you in the exam, little hint, any model that has this type of constructs, and I would ask you, would it be possible for the inductive miner to give you a model that describes the exact same behavior? You should by now know that this is not possible, because process trees simply do not allow us to express this type of conditional behavioral constraints. Alright, that was a big sentence. So this is a model that I actually mined of this data using language-based region theory, which we're going to discuss today. And the nice thing with this model is actually that it has sound word format. So in some cases we can even give sound word formats using region theory, not in all cases. Alright, so that's again a motivation why inductive mining is nice, often used, but it's not the answer to all of our process discovery problems. So let's take a look into language-based region theory. So I hope you kind of remember that region theory stems from pattern net synthesis, where we have a behavioral specification B of process, which is either a transition system or language. And the question is, can we come up with a pattern net that somehow describes similar or equal behavior with respect to that specification? And similarity in behavior, again, I had to typo because I didn't have time to fix it. is simulation, bisimulation, trace equivalence, or isomorphism, depending also on what type of specification you use. Now, what we're going to look at today is languages and sort of trace equivalence in the sense that we try to find BatteryNet that has the exact same language as the input language. And if that is not possible, so that's what basic language-based reason theory tries to do, if we cannot find a BatteryNet that describes the exact same language, so in terms of firing sequences, we try to find a model that minimizes the additional behavior as much as possible. So in some cases, we're not able to find BatteryNet that is going to give us the exact language, but then we want to minimize the additional behavior described by the model that we find. And to explain this region theory, I start with a little philosophical idea that if we have this event log describing A, B, C, D, and A, C, B, D, then if I add this place here, I guess we can all reason that the BatteryNet I'm showing now does not allow us to fire transition A, because it has a place connected to it by means of an incoming arc, and that place does not contain a token. And also, there's no way for us, except for manipulating the initial argument of this BatteryNet, to put a token in this place. So in principle, in this BatteryNet, we're not able to replay this event of A, B, C, D because of the fact that we're not able to fire transition label A. We are, however, able to fire B, C, and D anytime we want, any number of times. So essentially, what we can deduce from this is adding places in principle always constrains the behavior described by a BatteryNet. And if you think about this a bit further, the most, let's say the least expressive place would be this flower place that's also described by the inductive mind. I don't really have a slide of it, so I'm going to draw it to make this lecture so much more interactive. Amazing. So if we have this beautiful 4 transitions here, basically we can do whatever we want. So the least constraining place that we can add would be this place that we call the flower place, because someone thinks this looks like a flower. This is the least possible constraining place we can add. We can of course add an arbitrary number of tokens here, whatever we want. But once we start removing arcs, in this case, we're going to be equally, let's say equally less constraining. But if I remove this arc, I remove this arc, and now for the sake of having fun with white hands, I also remove those arcs. You see actually that I'm generating a more constraining place. So, because if we remove the tokens to get even more constrained, now I can only fire B if I already fired C. So in principle, adding places to any BatteryNet in general only constrains the behavior more. We can do less. And this is the conceptual idea behind language-based region theory. So if you understand this, the rest will also be understandable. So obviously, if we add this place, this is not going to allow us to replay the event data that we have here. However, if we put a token there, this is allowing us to at least describe everything here. It's still not allowing us to describe exactly the same behavior because we still have completely unconstrained behavior here. But in principle, we limit firing A once. Now, I can also add this place. And again, if I add this place, and we look at the behavior here, we observe that this place is constraining behavior of the battery net, but it is in no way violating these two traces. So adding this place to this completely unconnected battery net is totally fine, and the same holds for this. However, this is actually what I'm saying is not wrong here. If we add this place, we have a problem. Because we need to fire A twice to be able to fire both B and C. And if we look at the input data, we describe that firing A, or let's say when observing A, after that we can observe both B and C. So somehow this place is a place that is not in line with the input behavior. And essentially, if we look a bit back, so we've seen all these places that are fine, and if we start combining those places, for example, this collection of places, we create a pattern that exactly describes the behavior here. Now, in essence, this is what we do in language-based regions. So when using language-based regions, we're trying to find those places that somehow constrain behavior in such a way that adding them all together, they still allow for everything in the event log, yet constrain to some degree the behavior of the pattern net as much as possible. However, there's in principle a general problem. It is that if we go back to this place, this does not allow us to replay ABCD, ACD, because as I just explained, we need to fire A twice. At the same time, if I add a token there, we do allow for firing ABCD, ACD. So this indicates that on the one hand, there's several places that allow us to replay ABCD, ACD, yet at the same time, we're not always interested in adding all of those places. Now, to give another example of this, if we now change the event log, basically describing a choice between B and C, we have A, B, D, and ACD. This place is nice because it does allow us to, after firing A, either do B or C, which is exactly reflected in this event. At the same time, the place that we just saw in the parallel case also constrains this combination in such a way that we're still able to fire both A, B, D, A, C, D. So also in the case where this place in general is fine, there exist other places that if we construct battery net in the end, we would not like to have. So essentially what we do and what we will see is when we get the event log that looks like this, we're going to navigate through what we call this solution space of possible places that we can add such that we can come up with models like this. And essentially we do that like in state-based region theory by the notion of regions. And this slide essentially depicts what a region is in language space theory. And I'm going to read out loud what it says. Definition 3.1. Bracket, region, bracket close. A region of a prefix closed language where it's L over T is a triple XYC with XY in basically being a binary vector over T and a C which is either 0 or 1, so that for each non-empty sequence W is W2 prime concatenated with A and L, by the way, a mistake by the author of the paper, which is not me. Such that W prime is in L, A is in T, such that C plus the sum of t over t, w prime t times x t minus w t bigger equals 0. Okay, I can imagine that you feel like this. If you see that, and if not, then you really did your homework very well. So what it says is, given a place P, essentially, if you translate the region to a place, which we also do in state-based regions, given a place P and a trace T in an event log. So T here is a bit different from the T here. Place P can never contain a negative amount of tokens at any point in time when we're playing trace T. That's essentially what this is saying. And to replay every trace T in the event log, we need to generate each prefix. So after each possible prefix that we can generate of the trace, the number of tokens in the corresponding place, which is actually identified by this region, cannot go negative. And the funny thing is that Lisa, who also is the instructor of this course, recently devised an alternative algorithm which works with the same principle. So reading theory is not bad. So, as I showed you before, what does this basically look like? We have a bunch of decision variables. First decision variable, so as I said, a region corresponds to a place, and we have a set of decision variables. Those decision variables can all be either 0 or 1. So the first decision variable is denoted as C, and C indicates whether or not we want to put an initial token in the place we're going to construct. So if we have decision variable C put to 1, that means we put a token there. If we do not put it to 1, so we put it to 0, we do not have a token. Then we have two vectors or tuples of decision variables x and y. And basically, x maps to incoming arcs. So if we say the x value of A2 or A1 is 1, that means that we connect the transition with that label to the place. So it has an incoming arc from A1 if the x variable of A1 is 1. And the same holds for the y variables, but the other way around. So essentially, and I don't think that's on this slide, as I said, we have a lot of decision variables, and if we take a look at the place here, which does not contain a token, then this decision variable C is 0. Let's take a look at the x variables. So it has an incoming arc from A1. So the x value of A1 is equal to the x value of A2, because it also has an incoming arc from A2 and it has an incoming arc from C1. They all have value 1. All other values of x, so x of E is the x of F 0. And as I said, we also have a decision variable which we call y, which represents outgoing arcs. So the y value of C1 is the y value of B1 is the y value of B2 is 1 because we have outgoing arcs with B1, B2. So we have a set of decision variables. It's very important that you now understand that also all other y variables are 0. It's very important at this point that you understand that a place corresponds to an assignment to the decision variable C, X, Y, because later we will use that in more detail. So, as another example, this place I can again translate into these decision variables that I talk about. This place has no token, so we have a C value 0. It has one incoming arc from a transition with label C. So the x value of, let's call that transition C, is 1. All other have no interaction with the place, so the x A is the x of B, is the x of D is 0. For outgoing arcs, it has one outgoing arc to B, so the decision variable YB is 1, and all others are 0. Does now everyone understand how you can translate the place into an assignment of decision variables C, X, and Y? Yeah, it's not so difficult. You can also do the other way around. If I give you a random assignment of these decision variables, you should be able to draw the place. So if we all understand that, let's continue.
YC is 0.
Sorry, what?
YC is 0.
YC is 0.
Yeah, equal to 0. I mean, you just give the assumption that C is equal to 0 and you...
Now I take this place. It has no token. That the C decision variable represents a token being present or not. So if I put a token, then the characterization of this place in terms of the decision variables would be C is 1.
Yeah, but how about the X?
The X represents incoming arc. And since this guy only has an incoming arc from C, the X value of C is 1, and it has no incoming arc from A, D, and B, so the X value of A, D, and B is 0. The Y represents the outgoing arcs. It only has an outgoing arc to a transition called B, so YB is 1. It does not have outgoing arcs to Y, to A, C, or D, and that's why the Y value.
That's what I understand. Okay, but I want to say if C is equal to 1 or C is equal to 0, so it makes no difference actually.
Yeah.
To the equation.
If the Y value of C is equal to 1, it means I have to add this arc. Because the Y value represents outgoing arcs of the place. So that's the difference.
No, she met with the first C, the counter for tokens.
This.
Yeah.
Yes.
What do you mean?
I mean,
This C.
yeah,
Okay, let's call this M.
same.
The only reason I wrote papers about this, I use the word M because I think C is confusing. But the pictures come from a different paper.
What's the difference? Is M equal to 0 or if M is equal to 1?
Well, so this C here refers to the C which is now an M, refers to putting a token here. Yeah, so now I have a token here, so this variable M is 1. If I remove the token, there's no token, so it's 0. So it's I know it's a bit inconvenient that we use the C. I don't know why they picked the C. But that's the idea.
Is this M is used anywhere in the formula or?
Yes, it is. It's well, it's a C here.
And how we can calculate W dash?
What? Sorry?
W of t?
Yeah, I'm going to explain it later, but I first want you to be able to translate the concept of place into these decision variables and the other way around. Because if you don't understand that, the rest is going to be completely gibberish. So, because, let me just make an example for you guys. Slides are so 2018. So, since I'm going to make the lecture a bit more interactive, some slides you'll see later are going to be double, but I think this works better. So, if I have this very simple event bar with two traces, AZ, ACD, we now know about our decision variables. I kind of explained them. We have this X and Y and C, CQM. We say a region of a prefix goes language L over T. T here is the alphabet, so T would be A, B, C, D. So the triple XYC is a region if this underlying thing C plus the sum over T in T, W, blah blah blah, holds. Now, let's first create the prefix closed language. The prefix closed language is the set of sequences that's either a prefix of any of those two or a prefix of such a prefix. So the prefix closed language is this weird L, is the set of sequences, and I'm going to build it up from big to small. We have ABD and ACD. The prefix of ABD is AB. Prefix is just remove the last element. So we have sequence AB. Prefix of ACD is AC. Prefix of AB is A. Prefix of AC is also A. Prefix of A is the anti-sequence, which we write like this. This is our prefix closed language, L on the basis of the event. Now what this says is for every non-empty sequence, W is W prime followed by character A. This formula has to hold. So which of the elements of my prefix closed language are non-empty? Well, this one is empty sequence. These are all non-empty. But I have to characterize them as W prime followed by A. Meaning that ABCD is characterized by AB followed by D. ACD is characterized by AC followed by D. AB is characterized followed by A followed by B. AC is characterized by A followed by C. And the most tricky one, A is characterized as anti-set followed by A. Anti-sequence followed by A. Now, for each non-empty sequence, W is W prime followed by A, that's basically these guys. The formula has to hold C plus sum of T in T. So for convenience, let me write T as well. So, for every of these guys, formula C plus T and T, and then the big thing needs to hold. Let's write it down. And I start with the bottom one is A. So we take a look at this guy. We say this part of these characterizations is W prime of the formula, it's the prefix, and this is the trailing A. To make it more confusing, we use A. But it's this guy. So what does it say? For each of these guys, C plus big sum of T in T, and then this thing. What this actually says is take each element of T. So take A, B, C, and D. Count the occurrences of that element in the W prime and multiply that number of occurrences with the decision variable of that same T. So let's start with A. So we were working with the shortest characterization of the prefix A. So the W prime of the prefix A is the anti-sequence. So the number of occurrences of A in the anti-sequence is 0. So we have 0 times the decision variable x of A minus the W value of A, which is the whole sequence, times the Y value of A. So, in the sequence A, the symbol A occurs once. So, I have this C plus W prime T times XT, which was nothing. In the sequence A appears one time, so I have to multiply 1 times the Y value of A, so times minus 1. This minus, so basically 0 minus A is generated for the first symbol of T, for this prefix. Now we continue because this sum ranges over all elements of T, so for B, I observe that the empty sequence does not contain B. The sequence A does not contain B. So 0 times the XB minus 0 times the YB is added here. I do the same for C. The empty sequence does not contain C. So 0 times the X value of C minus this one also does not contain C, so 0 times the Y value of C. And the same holds for D. So for the first prefix, which is this guy, the smallest prefix, I generate this constraint. C minus YA should be bigger equal 0. So I now handled this guy. Let's say OK. But we have to do this for all prefixes. So for AC, we do the same trick. C is always there. For AC, the prefix of AC is A. So W prime is A. A occurs one time in sequence A. So according to the formula, I have to add one X A. And A is also occurring in the whole sequence AC. So I also have to subtract YA. B does not occur in the prefix of AC, W prime, and it also does not occur in AC itself. So we don't do anything. C, however, does not occur in the prefix of AC, but it does occur in the whole thing once. So I subtract YC, and D obviously does not occur in the prefix of AC, which is here, nor the thing itself. So I don't do anything with that. If I do the same for the prefix AB, I get C plus XA minus YA minus YB should be greater than 0. If I do the same for ACD, I will get C plus XA plus XC minus YA minus YC minus YB should be greater than 0. And for ABD, I get C plus the X of A plus X of B minus YA minus YB minus YD greater equal 0. So you get this bunch of constraints, which I admit you cannot really read anymore because this crap. But based on the simple event arc that I just shown you, we get 1, 2, 3, 4, 5 constraints in terms of our decision variables. Now, if we assign values to these decision variables, being put C to 1, put outgoing arc to A, then everything else is 0. So place something like this. You all know now that this place is characterized by C is 1, I can start filling out these values here, right? So I can say C is 1, YA is 1. So 1 minus 1, it's greater or equal 0. Nice. C is 1, XA is 0, YA is 1, YC is 0. 1 plus 0 minus 1 minus 0 greater or equal 0. So basically, by translating the event log into prefix closed language, and then generating constraints on the basis of our decision variables, gives us a description of which variable assignments are feasible in order to be able to still replay the trace, and all the traces in the log. Because, for example, if we would characterize the place B to A, meaning a no token, so we have XB is 1 and YA is 1, you'll see that the first constraint will not be satisfied. Because C is 0, we don't put a token in that place. YA is 1, so 0 minus 1 is not bigger or equal than 0. Okay. Let's see. This I explained. Great. This I also explained. Yeah. So you can also, let me first ask, who is totally lost? Don't be shy if you're totally lost. I was when I read the paper first. Who is medium lost? Medium lost, okay, that's good.
Next question.
Yes.
So there are probably many solutions to the linear system right here. And is actually the set of these solutions exactly the places? And then the vectors which describe the solution and also describe like which are the ingoing and outgoing arcs?
Yeah.
Is it like one-to-one or?
So the set of all variable assignments of these variables basically describes the solution space. But those are all places that you could add that potentially allow all the. That's not what you want to do because you get huge projections. So let me see.
So, in general, you can actually, these allow for models that actually allow more to be accepted than the event log is asked for.
Yes, but if you would add all the places, also referring to the previous question, you get a model that minimizes the additional amount. But you're right. So it is. Sorry?
There are probably more places than we need.
Yeah, much more. Yeah, so for those of you that have somehow familiarity with systems with linear inequalities and equations, this is not so hard. If you don't, this is a bit harder. So what you need to know now is the following thing. I've been telling to you about decision variables, namely one representing whether there's a token or not, which sometimes we call C, sometimes M, and variables X and Y which map transitions or basically labels representing incoming outgoing arcs. And the idea was that if we have an event log, we can generate a set of equations basically that have to hold for any assignment. And let me see if I have a concrete example in the slides. Because to show you matrix forms. Yeah, this is a good example. This is another example where we have an even similar event log. So we have event of A, B, BA. The prefix closed language is the empty sequence. I hope everyone can see that. A, B, A, B, B, A. So why? Because B is a prefix of BA, A is a prefix of AB, Now, as I already did here, what we want to do is we want to take all the non-empty elements of the lowest set. So the non-empty are A, B, A, B, B, A, and we want to generate constraints. And these constraints were formed like this. C plus the sum of T and T, WT. But what it actually means is, take this first guy, sequence A, take its prefix, the empty sequence, multiply that with the x vector or x variable of all the different letters, and use the number of times it occurs. So, because A does not occur in the prefix of the sequence A, we don't add the x component. However, A does occur in the whole prefix here, so we subtract the y component. Same for B. The prefix of B is the empty sequence. That means that A and B do not occur in the empty sequence, so we do not add an x component. We do subtract the y component on B because B is in this sequence. For AB, the prefix of AB is A, so it means that we have C plus the x component on A, because A occurs once in the prefix of AB, and we subtract the YA and the YB because both A and B occur once in the sequence AB. The last constraint is C plus the x variable for B, because B is the prefix of BA and B occurs once. For the whole sequence, B and A occur once, so we subtract YA and YB. An alternative way to think of this is C and all the x variables are the potential number of tokens you generate in the corresponding place that you construct prior to firing the last event or activity, in this case, of the sequence. So, if you look at A, we can put a token in the place. That's why we have the C variable for the first constraint. But before A, nothing happened. So there was nothing that could put a token in that corresponding place. So we do not use the X components because the X components, they refer to incoming arcs of the place. Then the Y components, they describe the consumption. To be able to fire A, we need to have an outgoing arc to A, so we put YA to 1, because we need one token for A. Same holds for B. We do not have anything that can contribute yet, because B is the prefix of B is the empty sequence, so nothing produced tokens, we could only initially put a token, and we subtract YB. If you look at AB, so what I said is the C and the X refer to the production side, so if we look at AB, to be able to fire B, we can have a token because we put it there initially and because A has contributed 1 to the place and B will remove 1. But we also need to remove the YA component because to do A, we also need the token. And the same holds for B. Essentially, when you practice a lot with constructing these constraints, you'll start seeing the pattern on how to construct them. Let's have a short break of 10 minutes, because there's still a lot of stuff.